right, go ahead and have your notebooks out and open to the Axioms and Postulates section. I'm also going to want to check informal statements. So I have it both places where I can check. There's first 9 axioms. Good. There. What? And the postulates were right there with the axioms, so that's actually what I wanted next, was right behind them. There's those postulates. Excellent. All right, formal statements 2 through 14. Good use of shorthand. Axioms 1 through 9, and postulates 1 through 5. Good. Axiom singular.
Yeah, I did feel like right on.
And postulates plural. I like the postulates plural better. And then informal statements. There's 2 through. Pen ran out of ink? Yeah. Didn't have another black pen?
No.
Black and blue? Alright.
That's my color.
Alright, axioms 1 through 9, postulates 1 through 5, and informal statements 2 through, hold on, I wasn't finished counting. Through, now you can turn it. 14, very good.
Mine looks like hieroglyphics.
Hieroglyphics? Hieroglyphics, yes.
Hierogeography.
Okay.
Or geometry. I get those two mixed up all the time.
Okay.
This is geography class.
All right. Let's go ahead and review over some of those things. You can set your notebooks aside now. And what is an axiom, Kendall?
Statement.
It is a statement. Good.
Yeah.
Just any statement?
That's like not. I mean that.
Chris?
Isn't it a theory based on
Not a theory. It's a statement.
a statement based on other unprovable facts? So like unprovable truths.
A statement that isn't proven but it's believed by everybody.
Okay, accepted without proof to be true. There we go. So it's the unprovable fact, right? It's the unprovable statement, an axiom. So a general statement, okay, it applies outside the realm of mathematics. In some cases, it applies outside the realm of geometry, certainly. But a general statement that's accepted without proof to be true. As opposed to a postulate, Genesis, which is just like an axiom, except what's the only difference between an axiom and a postulate? Audrey's really hoping you get this. Audrey! Chris?
It can only be used in the realm of geometry.
Good, it's a geometric assumption accepted without proof to be true. So postulates are geometric statements specifically. Axioms can be just general statements, but both of them have to be accepted without proof because they're so basic you can't even prove them. We use then these axioms, these postulates, we use definitions of things to prove other very simplistic fundamental statements, but they're not unprovable fundamental statements. And those statements were the informal statements that you copied down last night. We talked through, if you'll turn in your textbooks to page 41, we talked through the first 9 informal statements and essentially went through and proved them briefly because the proofs were brief. Again, I don't want these are not something we're just like, well, it says so, so I guess it's true. No, I showed why it has to be true so that we can know in good faith these are statements that rest proven upon other things. We're going to pick up with informal statement number 10, and let's have Ethan read that for us.
The sum of all the angles about a point on one side of a straight line through the point of a straight angle.
All right, the sum of all the angles about a point on one side of a straight line through the point is a straight angle. So we have a point. We have a straight line that goes through the point. And about this point, on one side, either above or below, I'm going to go above, we could have a whole bunch of angles. Angle 1, angle 2, angle 3, angle 4, angle 5, whatever, right? You can draw any number of angles that you want. This informal statement says that if you were to add all these angles together, it would always equal a straight angle. Well, again, on the surface, you'd be tempted to say, duh, but why? Why must it add up to a straight angle? Well, if we call the point O, and let's just call the line AB, the whole angle, because AB is a straight line. Again, that's the premise of the problem, right? Is that if you have a straight line through a point, so we're establishing, okay, AB is a straight line, well, therefore, by definition, then this whole angle's sides form a straight line. Therefore, class, angle AOB must be a straight angle. But why must angle 1 plus angle 2 plus angle 3 plus angle 4 plus angle 5 be a straight angle?
Because they all are based on the straight angle. They're all on top of the straight angle.
Let's use a statement that we've previously either accepted or proven, or perhaps a definition. The rest of you are thinking as well, because he doesn't care coming to you. You might be looking back, perhaps.
Good, I was about to say, I don't know if you want us to do that next.
Yeah, sure.
Is it like an axiom postulate?
Yeah, Fred, I would think axiom. We know that angle AOB is a straight angle. We want to show that all these other angles added together have to be a straight angle.
Is it a quantity may be substituted for its equal in any process?
We are actually going to use that, but Ethan,
The sum of all the angles equal a straight angle. Based off of informal statement. The sum of the 5 angles is equal to 1 straight angle.
where did you get that?
Informal statement 1.
Didn't that say the sum of all the angles of a triangle is a straight angle?
It did, but
But that's not a triangle.
But okay.
And informal statement 1 we didn't prove anyway.
But still.
How about this? This angle AOB is made up of several parts. One of its parts is angle 1, another part is angle 2, another part is angle 3, another part is angle 4, another part is angle 5. Now, Chris?
The whole is greater than any single one, or the whole is equal to any one of its parts. Equals any single one of its parts. Alright, the whole is equal to the whole is greater than any of its parts.
The whole.
The whole is equal to the sum of all.
The whole is equal to the sum of all of its parts. We know that angle AOB must be equal to all of its individual angles, however many there are, added together, right? I could have made more, but that angle is going to be equal to all the different angles added together. By substitution then, since angle AOB is or equals a straight angle, and AOB is equal to this, well, these two quantities are both equal to the same quantity, or that is, we could substitute, as Chris said, 1 plus 2 plus 3 plus 4 plus 5 in here for AOB because it equals AOB. So then angle 1 plus angle 2 plus angle 3 plus angle 4 plus angle 5, and again, however many angles you happen to have, we chose to have 5, must equal a straight angle. Now again, it's kind of common sense, but it's also provable, which is why it's not an axiom or a postulate. In this case, I guess it would have been a postulate, but it's not. It's provable based on previous statements. Informal statement number 11, Audrey, read that for us.
The sum of all the angles about a point is equal to 360.
And what I'd like you to do there, actually, if you would, in your notebook, I don't like the use of degrees there. Is equal to 360 degrees. I prefer technical terms because those are more usable in proof. I'm not sure why the book did this. The sum of all the angles about a point is equal to a straight angle. Or excuse me, a paragon, excuse me. Is equal to a paragon. Last problem with straight angle. Is equal to a paragon. So in your notebook, cross out where you said 360 degrees and write a paragon. It is the same thing, but one's a definition, one is based on measurement, if you will. And we'd rather not use measurement-based terminology here. So the sum of all the angles about a point is equal to a paragon. If you add up all the angles here, it must equal a paragon. The proof here is very straightforward. What is a paragon, class? An angle whose sides form one complete revolution. Well, if where you start and where you finish is the same point, you have by definition completed a revolution, which is therefore a paragon. So the sum of all the angles about a point is equal to a paragon, no matter how many of them you make. 3, 3b, 3c, okay? All these angles, you add them together, no matter how many there are, will always equal a paragon because of the definition of a paragon, an angle whose sides form one complete revolution. Informal statement number 12. Genesis, read that for us.
If the sum of two adjacent angles equals a straight angle, their exterior sides form one straight angle.
If the sum of two adjacent angles equals a straight angle, their exterior sides form one straight line. So here's angle 1. Here's angle 2. And we're told that angle 1 and angle 2 are adjacent, first of all. To meet the qualifications of here, they would have to be adjacent. And their exterior side, and they must equal a straight angle. So we know that angle 1 and angle 2 are adjacent. What does that mean? Three things.
Same vertex.
Same vertex.
Same side.
Common side between them. Good. Common vertex, common side between them. So therefore, since the common side is between them, these two sides are referred to as their exterior sides. Not the internal side that's shared, but the exterior sides. We're also told that angle 1 plus angle 2 equals a straight angle, right? If the sum of two adjacent angles equals a straight angle. Well, if they equal a straight angle, then that means that added together, well, if we add them together, we get the whole, right? The whole is equal to the sum of all its parts. So if we call this A, B, C, D, okay, angle 1 or angle ADB plus angle 2 or angle BCD must equal the whole angle ADC, correct? But since angle 1 plus angle 2 equals angle ADC, and angle 1 plus angle 2 equals a straight angle, then angle ADC is a straight angle. And if ADC is a straight angle, by definition, a straight angle is an angle whose sides form one straight line. So since AD and DC are the sides of the straight angle, then AD and DC, or AC, must be a straight line. Make sense? And again, that one's almost duh, but again, it's not technically a postulate because it is provable based on definitions, axioms, and postulates. Turn the page. Informal Statement 13. Again, you're starting to see how the difference between a postulate, which is literally, you can't even prove it, it's so basic, versus, well, that seems so basic, but it is technically still provable, and you can still put together some chain of reasoning to explain it. Informal Statement 13, Kendall, read that for us.
When two straight lines intersect, the vertical angles formed are equal.
We've actually already proven this in class. I don't know if you remember when we went through this, but I want to run through it again while we're on the topic here, since we're calling it an informal statement where we hadn't previously. When two straight lines intersect, of course, we form adjacent angles and vertical angles. Call this 1, 2, 3, and 4. Give me any pair of vertical angles, Chris.
1 and 3.
1 and 3 would be vertical to each other. So we would want to prove that angle 1 and angle 3 are equal to each other. We know 1 and 2 are adjacent, 1 and 4 are adjacent based on their definitions. But we also know this, that this right here is a straight line. By definition then, this angle here must be a straight angle because its sides form one straight line. Therefore, since this angle is equal to the sum of all of its parts, this angle is also equal to angle 1 plus angle 4. Which, since this angle is equal to 1 plus 4, and this angle is equal to a straight angle, then 1 plus 4 must equal a straight angle. The same could be said, though, of 1 and 2 by the exact same process, right? This is a straight line, because that was the premise, right? That we have two straight lines intersecting. This is a straight line. Therefore, this whole angle here, the sides form a straight line. Therefore, this whole angle is a straight angle. This whole angle is equal to the sum of its parts 1 and 2. Therefore, 1 and 2, substitute in for it, must also equal a straight angle. And since all straight angles are equal, that was informal statement number 5, I think, something like that, then angle 1 plus angle 4 must equal angle 1 plus angle 2. But if we were to subtract equal quantities like angle 1 and angle 1 from equal quantities like angle 1 plus angle 4 and angle 1 plus angle 2, the remainders, angle 4 and angle 2, must be equal. And I just proved the wrong one. Sorry, Chris. Let's go with 2 and 4 instead. The proof would have been the same for 1 and 3.
It's okay, I'm a pro.
It's all good. But anyway, so vertical angles equal, so that's the premise we would use there. And then informal statement number 14 is pretty straightforward here, based on a single postulate. But informal statement 14, Audrey, read that for us.
The sum of two sides of a triangle is greater than the third side.
I will say this proof at this point is not as great as I would like it to be. There's a better proof coming for this basic premise, but take any triangle. And remember we showed that in construction, the longest side cannot be greater than the sum of the other two. So these shorter sides added together have to be greater than this. And that's what this is saying. The sum of two sides of a triangle has to be greater than the third side. Well, think about it. This vertex here and this vertex here. What is the shortest line that may be drawn between those two vertices? The straight line. That's this. Any other line or broken line or curve is going to be greater, correct? Per postulate 2. Well, if this is the shortest line, then that means that this, what we could consider broken line, must be greater. The broken line is the sum of the other two sides, so the sum of two sides of a triangle must be greater than the third side. Yes, sir?
Can you extend the baseline on that triangle real quick?
Sure.
Just
Which way? Left or right?
right.
Right.
Further.
Further? And it can be extended indefinitely or limited at any point per postulate 4.
Now the two sides aren't bigger than the one side.
They're 2 points.
This is not, this right here is not a side of the triangle. The side of the triangle runs from vertex to vertex. So if we call this triangle ABC, AB, that segment, is a side of the triangle. BD is not a side of the triangle, nor is AD a side of the triangle. That make sense? A side of a triangle, by definition, is the line is a line that bounds the triangle. BD does not bound the triangle, therefore BD is not part of the side. Good question, though. At least you're thinking. I like that. Any other questions on this? All right. Look over at the next page, page 43. Page 43. And look at number 3. Go ahead and read that for us, if you would, Ethan.
2 straight lines cross forming 2 pairs of broken angles, so that if one of these angles is 90 degrees, all are 90 degrees.
All right, so 2 lines, and they cross, so that one angle is 90 degrees, or a right angle. They want us to show that the other angles, I'm going to call them A, B, and C, show that the other angles also have to be 90 degrees. Well, one of the angles, very straightforward, there's an easy informal statement we could use here, class. Which angle? Has to be 90.
No, they're on the right. C.
What? B, the vertical angle. We already proved informal statement 13, vertical angles have to be equal when 2 straight lines cross. So if this is 90, that's got to be 90. That's really easy. How to prove that the others have to be 90?
I have 2 different things I think you could do.
Okay.
First off, they're 2 straight lines.
Okay, right?
So if they intersect naturally, you're gonna have a 90-degree angle.
If 2 straight lines intersect, you're always going to get a 90?
You're about to just make them diagonal. I know what you're about to do. I'm ahead of you. No, I'm joking. But it's forming a pair of vertical angles.
It is forming a pair of vertical angles. That is true.
So they all have to be 90. And also for that one specifically, if both of those are 90, then naturally C and A also have to be 90.
Why?
Because 90 plus 90 equals 180. 180 minus 360 equals 180 divided by 2 equals 90.
Okay, so 360, you're talking about a paragon, correct?
Yes.
Okay. This would form a complete revolution, which, using numbers, we would argue, right, that would be 360 degrees. And you're saying that these add up to 180 degrees.
Yes.
Which is a straight angle.
Yes.
How do you know?
How do I know it's a straight angle?
How do you know it's 180 degrees?
Easily, because it says 2 straight lines.
Okay. How do you know a straight angle is 180 degrees?
Because it's complementary. Or not complementary, supplementary. A straight line, it's 180 degrees. There's no possible way for it not to be.
I never defined a straight angle as 180 degrees.
Draw a straight angle that isn't 180. Draw a straight line that isn't 180 degrees.
That doesn't prove it. I'm looking for the proof here.
What do you ask? That makes no sense.
What I don't like is that the book used degrees in the first place, to be quite honest with you. I would have preferred they just said, if one of the angles is a right angle, prove that they're all right angles. Well, we can prove if this is a right angle, this has to be a right angle because they're vertical, and vertical angles are equal. So let's ditch the degree terminology here.
Okay, because they're both 90, that equals 180, right?
You're back to degrees.
No,
again.
I'm not. Alright, oh, that's true.
Is it if 2 adjacent angles equal 180, or if 2 angles equal 180?
You're using degrees again.
How am I using degrees?
You said 180. That's degrees.
A straight angle.
Okay, 2 angles equal a straight angle. Okay.
Then the other 2 equal a straight angle.
I got it.
Okay.
When 2 straight lines intersect, the vertical angles formed are equal.
Right, that's how we knew that if one of them's a right angle, that the other's a right angle. But how about A and C though? We're starting to figure out A and C. Like B, that's easy, right? One's right angle, the other's right angle, we're good. How about the other one?
How can you prove that it's not 90? How can you prove that A and C are not 90?
Oh, that's not the burden of proof. The burden of proof is prove that they are.
If you can't prove that they're not 90, then
not so, not so. That does, just like we said, remember yesterday, I said we cannot prove the Bible's true. but nobody can prove it false. But that doesn't prove the Bible's true. Just because somebody can't prove something wrong doesn't make it right.
The protractor isn't a geometrical instrument, is it?
No, it's not, which is why we don't use degrees, typically.
That's an
What is a right angle?
90 degrees.
No, what's a right angle? You can look it up in your terms definitions, no problem. What's a right angle? Yes. I was like, what is a right angle?
Angle formed when two straight lines meet to form equal adjacent angles.
Say that again. The angle formed when
Two adjacent angles.
when two straight lines
Two straight lines meet to form equal adjacent.
equal adjacent angles. Well, this given right angle and C are adjacent by definition. Common vertex, common side between them. So if this is a right angle, then we must have equal adjacent angles, and therefore this angle must be equal to that one. Therefore, if this is a right angle and these are equal, then this must also be a right angle.
So
Same for here, because these are also adjacent, therefore this must also be a
I was close.
right angle.
That.
The idea that they're equal adjacent angles because of the definition of a right angle. And that, again, I don't like that. They threw you off, Chris, to begin with by using degrees, and they should not have. Number 4, let's move on.
I'm just
In the drawing. No, don't be done. Don't be done. In the drawing, angle X equals angle Y. Okay, so we're told these angles are equal to each other. Whether or not they look like it, they're equal. If that is true, that they are equal, prove that angle M and angle N are equal. Yes, sir.
Because the exterior angle is equal to its opposite interior angles.
We didn't actually prove that.
Oh.
That's an option. We will prove that. Okay, so it is true, but we haven't technically proven it. We just observed it, and I said it was so, but we hadn't proven it
Because
yet.
if you do M plus X together, doesn't it equal 90 or 180?
We're using degrees again. Stay off degrees.
Alright. So we're trying to prove
So instead of saying 180, what should you say?
a straight angle.
Straight angle. Okay, why do M and X together equal a straight angle? Assuming M is an exterior angle, N is an exterior angle. Why do M and X together equal a straight angle?
Because they're both there. Because one's obtuse and one's
Their sides form one straight.
Their sides form one straight line. Right? This is a straight line, otherwise you couldn't have an exterior angle. So since there is a straight line here, then their sum must be a straight angle. Okay? You bailed him out there, Audrey. Chris, let's see if you can finish the thought here.
So it has to be N and Y also have to do it because if I made it,
For the exact same reason, right?
yeah.
Also a straight line, sides form a straight line, therefore we have a straight angle. Okay, so n plus y is a straight angle, n plus x is a straight angle.
Also, it's an equilateral triangle.
But it's not an equilateral. It doesn't say it's equilateral. In fact, it really doesn't look, again, granted we can't trust our eyes, but there's nothing in there to suggest it is equilateral.
But yeah, we proved it, didn't we?
What?
We proved it that they're equal.
We proved what?
Because if y and x are equal, then n and m are equal.
That's what we're about to prove.
Yeah. So didn't we just prove it? Technically.
Not yet.
Because if x and y, it says that they're equal.
Yeah, x and y are equal. They told us that.
Yes. So naturally, if they're equal, and m plus x. See,
Okay, Genesis, you're laughing, so you gotta bail them out.
They're laughing. The thing is, they're laughing, but I actually had the guts to raise my hand.
Right. So Genesis, now that she laughed at you, Genesis, bail him out here. Help him out. Let's finish the thought. How do we know M and N are equal? M and N. How do we know that they are equal? That's what it's asking us to show, that M and N have to be equal. They told us X and Y were. I feel like we're making this more complicated than we need to be. If M plus X equals a straight angle, then M plus X class, M and X class are, no, M and X are,
The straight angle.
they add up to a straight angle, therefore they are
Supplementary.
supplementary. Good. Angle M and angle X are supplementary, right? Similarly, anyone?
So that means y and n have to be supplementary.
Okay, angle N and angle Y are
And
supplementary.
we know that x and y are equal,
We know that x and y are equal.
so they're the same exact, I can't say degrees. They're the same exact angle, is what that obviously what it means if x equals y.
Right, that means they are equal angles to each other.
So if they're supplementary, and that supplementary means they add up to a straight angle,
Which we
M
set up
and
here.
N, M and N naturally have to be equal.
Why? There's an informal statement, find it. There's an informal statement I'm looking for,
The
find
sum
it.
of two sides of a triangle is greater than the third side? No.
No.
Supplements of equal angles are the same angle or equal.
Boom! We already proved informal statement number 9. 9. That supplements of equal angles are equal. These are supplements of equal angles. Angle M equals angle N. That's the idea behind proof. Find a statement that we've already either proven or accepted and use that to prove it. Good, let's move on. Number 6. Number 6. We've got that picture there. They say that RS bisects angle AOB. They want us to show that it also then must bisect COD. So we've got these two lines, AC and BD, and intersecting at point O. And we've got this line that runs through, and it runs through so that it bisects, that should be a B, it bisects angle AOB. Again, by definition of a bisector class, bisect means to divide into
Equal halves.
2 equal halves, right? So angle X and angle Y are equal halves of the angle AOB. Angle X and angle Y are equal because that's what a bisector does. So if we know for sure that this line bisects this angle, how could we prove it bisects this one? We know that X and Y are equal. We want to prove that it bisects this. That is, that it forms 2 equal angles, and the 2 angles are called M and N. So if we could prove that angle M and angle N are equal, then we have proven that RS bisects the angle. Thoughts on how we could show that M and N are equal? Chris, you've been helping me a lot. I want to get some other people in here, like Kendall. Yes, Kendall. For those who don't have the guts to raise their hand, there's the teacher who can call on them and put them on the spot. Coming this September, Kendall Martin in geometry class. Okay, doesn't sound like
Actually,
it's
it's pretty
good. Do M and N look equal? Not really. But do we trust our eyes? No. If you said they did, I'd say, but do we trust our eyes? And he still says either way. It doesn't matter whether they look equal or not. We're going to prove that they are if X and Y are equal. If this is a bisector like they say, then those would have to be bisected. That's what we're trying to prove. Audrey, are you Kendall's friend?